Good afternoon, everyone. And once again, I welcome our guests, speakers, and all the attendees present here.
Good afternoon,
For a
everyone.
second session,
Of the
and
day.
once again, I
We
welcome
have
our
Professor
guests,
Nivedita
speakers,
Patel as
and
the
all the
chairperson.
attendees present here.
Thank you, ma'am, for
Good
your
afternoon,
presence
for a
today.
second session. We have now reached the second session of the conference. To begin with, I invite Dr. Ishwaramurthy KV, Assistant Professor from Indian Institute of Information Technology, Design and Manufacturing, Kurnool, Andhra Pradesh, to throw light on non-invasive sensing of body fluids. Over to you, sir. Hello, sir. Sir, we are not able to hear you. Hello? Yeah, we are not able to hear you, sir.
Your mic has been muted. Please.
Hello, ma'am.
Yes, sir.
Hello.
Please. Yes, we
Yes,
can
ma'am.
hear you. Can can you please
Thank you.
share your screen,
Sure, sir.
please?
Sure. Good afternoon, everyone. Today we are going to see about about non-invasive sensing of sensing of analytes in the body fluids, right? So first, what is the broad line of our lecture? It is biosensor, and what are the current methods used in the biosensor? Need
Of the
And
for
day.
the
once again, I
continuous
We
monitoring,
welcome
have
our
Professor
guests,
platform
Nivedita
for
speakers,
Patel as
and
non-invasive
the
all the
invasive
chairperson.
monitoring, different types of sensing methods, selection of
Yes,
used
sir.
in the biosensor, need
Of the
and
for
day.
the
once again, I
continuous monitoring,
welcome our guests,
Your
platform for
PPT is
speakers,
not
and
non-invasive
visible,
all
sir.
the
invasive monitoring, different types of sensing methods, selection of used in the biosensor, need
Of the
and
for the
day.
once again, I
continuous monitoring,
welcome our guests,
Your
platform for
PPT is
sir, now visible.
No, sir, no.
Oh, no, sir. It's showing that I'm sharing the screen.
Yeah, it started somehow. Let's see once again. Wait for a second. Yeah, now it is visible. Sir, please go on, sir, please. Thank you.
So now you're able to see.
Yes, sir, now it is visible, sir. Please go on.
Sir, actually, I'm traveling.
Yeah,
The
I
non-invasive
will.
invasive monitor. I'm
Yeah, it
traveling now.
started somehow.
Okay.
Okay, let's see once again. Wait for a second. Yeah, now.
This broad outline of the presentation is biosensor and the current method, need for the continuous monitoring of body fluids, and the platform for non-invasive monitoring, different types of sensing methods, selection of which method and sensor. And coming to the basics of biosensors, and we need the human samples like blood, urine, and we have the food samples, and we have the environmental samples and agricultural samples. And to identify the particular sample, we need different types of biological elements. It may be enzymes, it may be antibodies, it may be cells, it may be DNA, and it may be a aptamer. To convert this biological element into some signal, we need a transducer element between that. So it may be by biological samples and biological element may combine to change this process into the electrochemical or optical, colorimetric, or mass or magnetic, right? Then after this, after we need to have the signal processing, then we'll have the display. So in this, main part is our biological element. In the biological element, we need to choose according to the what the sample we are going to choose. Let's say if you want to sense glucose, then we have to choose the glucose oxidase. And nowadays, the non-enzymatic sensors are available. And if let's say we can able to choose urea, it can be urase, and for cholesterol oxidase. And the transducer is mostly if you take the electrochemical and how this redox the potential of the particular material is it affects the products of the products where the reaction between the biological element and samples happens. So let's say for glucose, it is the main product is gluconic acid. Glucose oxidase, glucose goes to give gluconic acid H2O2. So we need to know what is the reduction or oxidation potential of H2O2. Accordingly, we have to choose the material for electrochemical so that it can be oxidation can or reduction can be happen at low voltage. So to avoid all the interference species. After that, we'll have different signal processing methods. Like say for electrochemical, we have potentiostatic, amperometric, or differential pulse potentiometry. Optical, we'll have simple Lambda-Wills law observance, and mass. If you is able to place it on a small micro MEMS cantilever, so we can able to change the natural frequency shift and magnetic material. So we have different according to the transmission principle. We need to do the signal processing. After that, we can able to have the display, or we can able to transmit to the long distance. Okay. Then in 1956, they have found this basic glucose sensor, and after that, we have to have the triage. It's a normal facility lab is we have the triage. We need to collect the sample, and we have to perform the test, and we have to compile the test result, and we have to analyze the test result. Then it is given to the patient. And after uh, minimization of electronics and
Excuse me,
invention of
sir.
new
Ishwarmurthy,
yes, sir.
sir.
Yes, sir.
Are you still on the first slide?
No, sir. No, sir. I'm in third
Actually,
slide actually.
unfortunately, we have been stuck up in only the first slide. Non-invasive
Okay.
sensing of analytics in body fluid.
No, no. I'm in third slide.
I don't know. It has been stuck up. It is the same for everyone. Can you come out of the slide mode and change and do it
Sure.
again?
Just a minute. are you able to see the screen? Hello, sir.
Wait, sir. I think it is taking some time. Yeah, now we can see the screen.
Now a biosensor screen, right?
Yeah, biosensor screen.
Okay, sir.
Don't go to the slide mode and you just say like this only, sir. You can change the slides.
Okay, sir.
Okay. Sir, please go on, sir.
Hello, sir. Hello.
Yes, sir.
Yes, sir.
We can hear you. Please go on, sir.
Thank you. Thank you.
Hmm.
Sir, the previous screen about the biosensors. So, what is the sample, biological elements, and translation principle different, and what is the signal processing? Then we are moving to the pathology lab versus point of care. So, after 1950s, the invention of basic biological sensor, there are different types of sensor came in, but the pathological conventional testing procedure involves we need to carry the patients and we need to carry the sample and we need to process the sample and we need to perform the test and we need to compile the test result and we need to analyze that test result, then we need to give to the patients. So it's kind of a laboratory process. Then invention of novel materials and miniaturization of electronics, we came to the point of care testing. So it is a simple sample collection, load the sample and analyze the result and give it to the patients. So the point of care device, it is not only available with the pathology lab, so can able to have with patients or a person who want to take the test. So it can be easy for any caretaker or a doctor to get that done immediately. Then again, this one came to the wearables, right? So again, the human invention not stopped with the POCT, the wearables. So in wearables, so the people want to know continuously. First, they have invented to monitor the activity. Let's say for jogging, how many steps. But become the fancy electronics. It came to the serious. So 2001, they have launched the glucose watch to monitor glucose continuous monitoring of the glucose. But however, due to this, some of the false results given by glucose watch, it was discarded 2007. Then the people are continuously working on that to make wearables to monitoring of the blood analytes through non-invasive mode. So what are the method they're using? So they're using a breath analysis and they're using interstitial fluids, they're using saliva and they're using sweat and they're using tear and they're sometimes they're using by wound. If there is any wound, they can able to monitor. So from pathology lab to POCT, they came to the. But there are few challenges to make to monitor through the wearables, right? So the single building can't able to fit in the single watch. So how they are doing now? So then what is the need for monitoring, right? So the pathology lab is that, POCT lab is that, POCT is that. What is the need for continuous monitoring? Let's say the glucose, we know that uh, glucose is not a disease; it is a metabolic disorder. One thing is able to maintain the glucose level in the blood, we can able to avoid major complications like nephropathy, retinopathy, neuropathy, and cardiovascular device. But how to maintain it? Only thing is, if some person is in uh, need to inject the insulin, So without taking food, if it take, then it is become it is may it will lead to some fatal. So if it is some person, if without taking, if is keep on taking the meal, if the glucose level goes to more than 500 600, this is also fatal. Only thing is the we need to make the continuous monitoring, so that we can periodically we have to inform that particular person what is our glucose level, then he can able to manage his diet as well as the insulin dosage. And if you consider acute kidney disease, so the people the periodically going to dialysis, whether they doesn't know their more than the threshold level, or some level is disturbed, every day for 2 days only they keep on doing the dialysis. But if you have continuously monitoring, that it can be controlled. So if some person is taking the food which contains more salt, it will bring down the urea, so that he can able to control the food. And whenever the urea goes beneath the threshold level, he can go for the dialysis. And again, if you consider the potassium or ions, then because the CVD and CKD is strongly inter intertwined, then we need to check the potential level, because the higher potassium level also, it is a high risk for the patients. And nowadays we are the people are start monitoring the cortisol. So the cortisol is an steroid, which is steroid hormone, which is used to segregate in the person. Whenever during the sleep, it will be in very low level. So yeah, as soon as the person wakes up, it is slightly is keep on increasing, and afternoon it will reach peak, and evening it tries to decrease. But the people who in the stress, the cortisol won't decrease, and it leads to some other complication. Otherwise, some other person cortisol won't even segregate. So these are the things we monitor. Let's say if the in soldiers, we have seen some papers around yearly around 150 soldiers are uh, uh, m- uh, attempt the suicide in the our army. So we can able to monitor the cortisol continuously. Who are the people are feeling stressed, they can able to monitor. And same time during the training we can able to monitor the cortisol level, how the person is taking the stress. And lactate is one more chemical analyte is need to be monitored. So it is not only used in the sepsis patients, it's mostly used in the neonatal ward also. So everything need to be monitored continuously, so that we can able to make diet and medicine, we can able to give the diet as well as the medicine properly to the patients. What are the current practices? We know it is a fingerprint method and venous blood and sampling, and otherwise via catheter sampling. So these are the current practices. So, but some of the things they have to do frequently, they're doing by this, but it is prone to the infection, and it is making a discomfort to the patients. And as well as for pediatric and for elderly patients, it will be like kind of a painful procedure. Okay, if it is not blood, then what is the other things we can able to do with blood? We have interstitial fluid, we have urine, we have sweat and saliva, ocular fluids, and respiration. That is, then whatever we are doing the inhaling, we are and after inhaling, all this waste are collected, and while exhaling, the air is mostly compressed of CO2 and other waste released by the body. So if you take urine, so this is mostly commonly collected clinical and non-clinical testing, especially due to ease of collection. Is a simple way of doing it. And what are the composition of urine? It is inorganic salts, organic compounds, and including proteins, hormones, and a wide range of metabolics, including glucose, urea, and sweat. So it is a primary biological role. Sweat is a biological role to for making the thermoregulation. And nowadays, the people are considering is most accessible for glucose detection as well as the lactate detection. And one more thing, compared to other body fluids, and it is most easily to access for sampling and sufficient quantity and rapid reproduction. So by having some with chemical, the people can initiate the sweat segregation. So that is also possible. And we should know what is the nature of the sweat. It is the acidic. And what are the metabolites we can able to monitor, like lactate we can able to monitor, glucose, alcohol, and uric acid we can able to monitor by the sweat, saliva. And it is also, it is an nowadays we can able to see it is an some attractive diagnostic fluid, because it is can be collected non-invasively without employing any specific device or trained people. And there are some studies, what is the correlation between the salivary glucose level and blood glucose level between the diabetic and non-diabetic. But non-diabetic, it is not matching with the blood glucose level, but they found that it is the diabetic patients, the salivary glucose level is correlated with the blood glucose level. And is become a, however it is a complex mixture, is about 99.5% of water and 0.5% of electrolytes like amylase, lipase, mucin, glycoproteins, glucose, and antimicrobial enzymes. Now the people are working, and it's become an alternative to the blood and the to measure the glucose and ocular fluids. So the Google is working on to make a lens to sense the glucose through the contact lens. So the ocular fluids not only is tears, it is also includes aqueous humor and vitreous humor, and which are the one of the promising fluids, because in this we can able to find glucose concentration is highly correlated to the blood glucose. And this monitoring of glucose also, this is kind of a new technique. And one of the thing is it is completely the invasive method, and it can be done with a continuous patient. So along with not only glucose, we can able to see mucin, lipids, lysome, and urea, sodium, potassium, and immunoglobulins, lipoclan, lactrin. All those things are available in the ocular fluids. So along with this, not only the ultrachemical method can be used, with microneedles we can able to use some optical coherence tomography, fluorescence spectrophotometry, ocular spectroscopy, and optical polarimetry can be used with this. Okay, but 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 if you have seen everything here, urine, so the collection is very difficult. Sweat, you need to do with ice, otherwise you have to add some of the chemicals to segregate the sweat. But saliva, you can't able to keep any device on your mouth, otherwise sampling by any means it will looks like wet. And ocular fluids, being an eye in a very sensitive thing, it is very difficult to keep any device on the eye. And the air, uh, nowadays, because the air is kind of a gas sensors or array of gas sensors, so they are being people are being working on it, because if you take TiO2, it sends all the materials, all the gases. But only thing is how we can make the particular gas is present. That is very difficult, and it will have so many interactions. This in hope, interstitial fluid is a fluid which all the cells in the body, it is baths in the interstitial fluid. if you consider the body fluid composition, we have extracellular fluid and intracellular fluid. In extracellular fluid, the it is we have the blood plasma and interstitial fluid. So interstitial fluid comprises about 15% of body. So what is the having advantage of the interstitial fluid? You can see here plasma and interstitial fluids, both the chemistries matches except protein. So it matches with the sodium, matches with the potassium, chlorine, and except the protein, it's going to match. Okay, what is the purpose of the interstitial fluid? So interstitial fluid is a responsible thing to give the energy or nutrients to the cell, and as well as, and it is going to collect the wastes from the cell also. So, but at arterial end of capillary, the blood pressure is 32 Hg. So all the energies is going to this tissues and cell. At venous end capillary, that net pressure is minus 7 Hg. So all the wastes are coming to it. Okay. So for choosing any analyte, let's say for choosing any fluid, body fluid, to measure something, we should know what is the blood plasma concentration level, and what is the interstitial fluid concentration level, what is the ratio, what is the time lag. So this is important actually. Let's say for example, we have taken glucose, urea, potassium. For in plasma, it is 80 to 110 milligram deciliter. In interstitial fluid, we can able to find 77.98 to 104.61 milligram per deciliter. And the interstitial fluid by plasma is 0.951. That is the time lag. So in the literature says only 0 to 15 minutes. Same thing like urea, it is exactly the ratio is 1 and the time lag is 0 to 15 minutes, and potassium is 1, and it says that the time lag is very less in this. So you can choose interstitial fluid, tear, saliva, urine, but we should know what is the time lag and what is the correlation and the ratio, right? That is the important thing. Okay, how we can collect the interstitial fluid? So there are some literature we are using, we can able to use microneedles, but we can use the microneedles, but the people used to say it is not an invasive method, it is kind of a minimally invasive method. So in previous days, we have the intophoresis. To have the drug delivery, we can able to load. Let's say we have to pass a small current, and the anode we can able to keep the positively charged drug. And if we pass a small current, this positively charged drug will be repelled to go to the bloodstream, right? So this simple electric current able to drive the it will gives the driving force, the primary enable penetration of charged molecule into the skin. But in we know this in electrical engineering, we need to maintain the electrical neutrality. So number of ions in above the skin, the conduction is going due to the electrons, and below the skin, the conduction is due to the ions. So number of electrons, ions is going into the body has to come out of the body, right? So it is kind of a symmetrical process. It will something has to go in and something has to come out. But our interest is what is going to come out, right? So if we able to analyze some of the some of the if we able to analyze component coming out, we can able to find what is the glucose in this, and if we able to correlate with the glucose in the blood sugar, then it can be used as a non-invasive method. So same thing, we are our interest is to analyze coming out of the body. So first is iontophoresis. First figure shows process of iontophoresis. Second figure shows process of reverse iontophoresis. So we are not in iontophoresis. Our aim is to deliver the drug. But second reverse iontophoresis, our aim is whatever collected, collected sample, we need to analyze whether how much glucose is present, how much urea or alcohol or potassium. Okay, what are the methods, transport mechanism during reverse iontophoresis? One is the passive diffusion, electromigration, electroosmosis. And what are the pathways, main pathways, how this ions are moving above the scene is non-abdominal pathway or with this is a sensor. So we are going to keep the collection this actually this converted PDF. So we keep the collection chamber. Then if the current is passed, this glucose ions comes into the cathode, because we know that our in the physiological pH, our skin is negatively charged. So this in the buffer solution, this moment of ions, positively charged ions, more in the cathode. So while coming above the skin, drags urea or glucose neutral molecules along with that, so that in the cathode electrode we will have the more glucose or urea. So these are another methods along with the reverse interface, because one of four is electromagnetic techniques, metabolic heat conformation. However, we can able to choose the reverse interphoresis because we can able to make sensing as well as extraction with single electrode. We're going to see that. Okay, if you make any sensor, let's say, if you not only for reverse interphoresis, we have to make, if you want to build a sensor for any non-invasive method, these are the steps we can able to do. Instead of reverse interphoresis, you can make any method. So we need to extract. We have to extract. Let's say extract the glucose or ISF or a saliva. Then we have to analyze whether your desired analyte is present in the in it or not, and what is that amount of uh, analyte presented. And sometimes, let's say your blood glucose level is 100 mg per deciliter, and the same won't be present in the reverse collected reverse interphoresis. It will be very, very small, right? So maybe ISF will contain the same, but while extracting through the transdermal process, while coming out, it will be decreased. So what is the modification standard method you have to do? Then after that, we know these things. Only thing is we have to do with in vitro studies by using some phantom, and you have to optimize the parameter. Here we need to optimize the parameter like current and area. And if you want to do the sweat, you need to collect the sweat. You need to choose how microfluidic looks like, how it is possible to collect the sweat, right? All those things. Then afterwards, you got it, and you have to go and human. So you have to do the proof of concept and what is the optimization of extraction of particular sample. Then after that sample can be analyzed, then you can say, okay, my desired glucose value is can you able to detect glucose value in that. Then after that you have to correlate blood glucose level and collected glucose level through the particular body fluid. Then you have to develop the sense. We know blood glucose level is 100 milligram per deciliter, but what is the sample? What is the level present in the body fluid? Whether let it be urine or a TN or what is the level? So accordingly, we have to build the sensor. Then we need to test the sensor with the particular function. Let's say if you want to do it with reverse interphoresis, you need to do with then you have to inject the current as well as you need to collect it. If you want to do it with sweat, then you need to collect the sweat and you have to sense it, right? So those are the things you have to do. Then with human clinical trial, you have to implementation. So in first we have tested with the phantom. So the bottom chamber will act as a transdermal, and both the chamber will act as an collection chamber. So then occurs two chamber will the collection chamber will fill with the buffer solution and separated by the cellular sustain membrane. It will act as an artificial skin, and we can able to use a PIC ES skin or a for this purpose. And for delivery of current, because the maximum allowable current is 500 microampere per centimeter square. So we need to get the optimize that. We have developed a programmable current source. Then we have done the in vitro studies. Then we have optimized the current, and by varying the subdermal glucose concentration and varying the extraction time and varying the current density, we have optimized in where we can able to get the more glucose and concentration. So these are the graphs. First graph shows the effect of subdermal concentration. So the concentration is increased in subdermal. This collection also is keep on increasing. Already we know that due to this osmosis process, we get more glucose. Cathode is keep on glucose level cathode is keep on increasing, and for extraction time also this glucose level is increasing, and the effect of current density keep on increase the current density, the glucose level is increasing. Okay, now we found that this is in vitro. Then we have to do it with human. So by getting the human ethical committee approval, we are done with this. Then we have used buffer and solution volume 0.7 volume and current density, and the extraction time is 100. Then we have to analyze glucose using color method. That because being an institute, they won't give more subjects for the study. So we have identified for subject one for different time period what is the glucose value and the extracted glucose. Though every human having more than 90 milligram deciliter, you can see here the extracted glucose through reverse kind of force is only 1 milligram per deciliter per hour, right? So because our skin will act as a resistant. Champion will give some buffer solution. What the IS solution will so we'll have glucose oxidase is immobilized. Then when glucose oxidase reacts with the glucose, it's going to give glucose reduced and take the electron. Then it can computation of glucose can be correlated with this. We have used so we have mediated, and it is being a counter electrode is a graphitic carboning, and the reference is silver chlorinating. These are the steps. The plane we have seen the PVC, then we made a conductor line, then we have put the reference electrode, working electrode, then counter electrode, then we have used the insulated material. So these are the different catalysts we have used. Prussian blue and cobalt phthalocyanine. This mechanism of reduction and oxidation of H2O2 is given here. So again we have to do this some material characterization, how it looks like. So the PBV, Prussian blue and CPPC, graphitic carbon, different electrodes, and we have to do the XPS because after material because it's done by the screen printing, whether this material is having this property or not, we have done XPS study. then we need to do the reference electrode, the stability of a reference electrode, because in electrochemical, that too uh, in analytical electrochemical, the stability of reference electrode is to be a vital parameter. So we have monitored for around 3000 seconds how it is open potential electrode. Then we have tested with the hydrodynamic voltammeter phase. So in which voltage it is going to give the maximum performance, that we need to do. Then we have studied that amphipmetric the screen printed electrodes with H2O2, both the things, both fusion blue and cobalt thiocyanin, and we have identified the sensitivity, range, reduction limit, and response time for the H2O2, and we have immobilized the glucose oxidase by using the cross-linking method. So we have immobilized using the cross-linking method. Then we have done amphipmetric glucose sensors by varying the glucose concentration. We have identified with what is the sensitivity of PB, SPB electrode with cobalt thiocyanin electrode, and we found that the sensitivity is slightly more than the thiocyanin, range with gas we are doing 90 to low range. In vivo, though the bit concentration is high on this, so we will wait for concentration reduction. That is, the limit of reduction should be very low. And one thing we need to test with the study. So for what is contribution of current or as contribution. So we found that from the dollars have then we have chosen the machine blue screen printed electrodes for the reverse interferences. Okay, now our sensor is ready, but how to make the to deliver the current? So we can then we can't able to keep the our electrode using electrode. The surrounding we can see that blue color. So this can able to have, that is extraction electrode, that is that's a for the delivering the current. Then same thing we have to use with the phantom. So same subdermal then it is separated by the cellulose sustainable. Then instead of the we use methyl cellulose, right? So which can able to, instead of solution we have used the methyl cellulose gel. Then we wait and extraction time and RNA. We can able to do both extraction electrode electrode is is working. Then we end for clinical investigation. So this is the protein we have, and we connected to the PC to the of sensor as well as reverse interferences to give the current. Another is here the cathode will be used through in cathode we can, so next we need to detect the baseline amphipmetric current for 60 seconds. Then we need to pass the current for 250 microampere per centimeter square for 30 minutes. Then we have to detect the glucose. So these are the subjects we have detected. And for what is the blood glucose level? So what is the glucose concentration is extracted, and in milligram and micromolar, and what is the flux? The glucose flux extracted by nanomole centimeter square by hour. This is the flux. Then we have correlated with the subjects. So with the different subjects 0.54. It shows that in this method can be used, but every person has to be calibrated. before the starting of the experiment. And this is the only small disadvantage in this, because all the person's skin won't have, skin may be have the same property, won't have the same property. It will have the different property. So if across the person, if you calibrate it, you can able to get R square values less. But in the, if you able to calibrate for simple person, you can able to get the more R square. So nowadays, instead of only making, instead of only with the reverse iontophoresis, the people are coming with observance spectroscopy, 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 because ocular spectroscopy from means to direct the glucose as well as some other analytes. So only thing is, first we know what are the first we have to start with partner analytics. Then we have to choose the body fluids. Then we have to, because if you choose non-invasive, then we have to go for only the main advantage going for non-invasive is continuous monitoring. Then we have to identify whether that particular fluid is going to available for 24/7 for continuous monitoring. Okay, if it's available, then it is keep any sensing methods. How to select the sensing method. So we can't be able to have the complicated optical method to keep it on a to attach to your body, or sensitive method we can able to can't we can attach to your body. So what are the sensing method you have to select? Sensing method for sensing method, which should be a, at last we should make kind of a wearable thing, whether it is a TD or electronic spot, to make it at last a kind of a wearable thing. Then we can able to do we can able to do the continuous monitoring of it. So these are different methods to so observe just where we can thought areas, and all those things are given here. Thank you.
So are you done?
Yes, sir. Yes, sir. Yes.
All right. So is there any question? I request the attendees to put forward the question in the chat box so they may unmute themselves and speak up.
Okay, am I audible?
Yes, sir, you
Yes.
are.
Okay, so can you go to the previous slide where you did the linear fitting to the glucose levels? Okay, so in the linear fit, you also are getting an intercept, which I was not expecting, because ideally it should go through 0, 0, or is it just the measurement error? Or
Sir, actually, it is done for the across the patient, different patients, different subjects actually. So different.
So what I'm trying to understand is the expectation is to get the blood glucose level to be same as transdermal extracted
Yes.
glucose,
Yes.
or they are okay.
Actually, we can't.
In that sense, the difference
Otherwise,
is too big, no?
yes. Yes, it's too big. But only thing is, for a person, we need to correlate. Let's say for X, yeah, for for X person, if the ratio of blood glucose and collected is 100, is not a problem. Always we can use the multiplication factor. We can able to detect. So whatever now they're doing that, first they will calibrate. Let's say they will do the reverse interferosis. Then they will collect the they will sense the what is the glucose level collected in the through ISF. Then they will go for the blood test. Then they will do the calibration. Then they can keep their sensors for 24 hours or 45 8 hours for continuous monitoring. So the first time the calibration is required for this reverse interferosis.
Okay, thank you.
Any further question? All right. So thank you so much, sir, for
Thank
such a wonderful and informative presentation. We'll move on to the next speaker. Next, we have a presentation on mathematical modeling of mechanics of fibrous scaffolds for tissue engineering applications. And to speak on it, I invite Dr. Suhail Rizvi Mohammed, Assistant Professor of the Department of Biomedical Engineering, Indian Institute of Technology, Hyderabad, Telangana. Over to you, sir.
Can you see my screen?
Yes, sir.
Okay. Okay. And you can also see the transitions.
Yes, sir, perfectly.
Okay, thanks. Okay, so thank you for the introduction. And before I start, I would also like to thank the organizer for arranging this wonderful meeting and also giving me the opportunity to present some of my work as well. So as most of you have attended the first talk in the morning session, so you have heard about the fibrous biomaterials. So here again, I would like to just emphasize the importance of the fibrous materials in which are found in nature and which range from, say, uh, which range from the cytoskeleton, which is found inside the cell in the form of actin and microtubule fiber, and also in the extracellular matrix, which is collagen and and the elastic fibers are part of some of the tissues. And also in if we look into the plant and other system, we also find some other examples of the fibers in the form of cellulose and, say, spider silk. So this ubiquitousness or prevalence of these fiber materials in the nature has also inspired the use of such materials for bioengineering or specifically the tissue engineering applications. And here I'm just showing a couple of examples where these fibers are fabricated using electrospinning method. And as you have listened the first two talks in the morning session, so these materials are widely used in as scaffolds in tissue engineering and also as drug delivery particles and also filtration media and many more. And since this is a bioengineering conference, and I believe many of you will remember this paper from Dennis Disher group, which they have shown that when they put mesenchymal stem cells on on substrate with different mechanical properties with different elastic modulus, they find that the stem cells actually differentiate, and the final fate of the cell actually depends on the mechanical properties of the underlying substrates. So, for instance, in case of a very soft substrate, the stem cell differentiates to become a neuron. In a moderately stiff substrate, the cell differentiates to become a muscle cell. And for a very stiff substrate, the cell gives an osteogenic response and becomes a bone cell. So this actually highlights the requirement of the importance of the mechanics of the scaffolds which are used in tissue engineering or in general bioengineering applications. And the mechanics is not only limited, and the effect of mechanics of the substrate is not limited to only the lineage specification, but there have been tremendous amount of studies which have shown the effect of substrate mechanics on, say, cell proliferation, migration, the spreading of the cell when they are put on a substrate, cell polarization in the form of asymmetric localizations of different proteins. And in addition to the mechanics, there is also an underlying structure which you can see, which you can see in the previous slide. So there can be different arrangements of the fiber. So one can have scaffolds which may be of fiber or which may be of some other nature, but the arrangement of its constituent can be of different types. So you can have a fiber scaffold where the fibers are arranged in a random order, random manner. So there is no fixed arrangement. and then you can also have a scaffold where fibers perfectly aligned in a given direction as well. So that is one to differentiate between different substrate structures. And it has also been found that the structure also influences the behavior of the cell when it comes in contact with it. So there have been works which have shown the effect of substrate structure or substrate architecture on the morphology of the cell or cell alignment, whether in case of an fibrous scaffold, if the fibers are aligned, then cells which are put on it also tend to align. But I mean, it also depends on the type of the cell, but this is a general result. And also differentiation and migration. So I mean, this whole slide is just to emphasize that the understanding of structure and mechanics is structure and mechanics of any biomaterial is essential for their use as tissue engineering applications. So how do we study the mechanics of such systems? So there are primarily two approaches. One is you can have a sample of such material and you can perform some experiment. You can apply forces and look how it deforms. And by correlating the deformation with the forces which are applied, you can get a sense of what its mechanical behavior is. If for a given amount of force it deforms too much, you can guess that the material is not too stiff. If for the same amount of force it deforms, you can have an idea that the material has higher elastic modulus. Or and this experimental characterization of such systems actually is, as you can expect, that it is also resource consuming as well as time consuming. But this does not mean that the experiments are replaceable by any way, but they can be supplemented or they can be complemented by another approach of mathematical modeling, where one can take into account the different ingredients of the material, which we can know by way of, say, imaging or other means, and apply some and use the power of mathematical modeling to estimate or to make to estimate or analytically obtain what, for a given structure of a material, what will its mechanical behavior be. So in that sense, these two approaches are complementary, and because mathematical models can never work if there is no experimental data. And similarly, once we have some mathematical model of a given system in our hand, we can use the knowledge which we gain from this model to design better materials. So so today actually I'm going to present some of our work which we have done using mathematical modeling to understand the mechanical behavior of these materials. Uh, okay. So the question is, what is mathematical modeling? How can we use mathematics to understand the mechanics? Because those are two different things. So, so the understanding of mechanical behavior of any material is basically the bread and butter of the whole of mechanical engineering. And in most of the materials which we deal with in our day-to-day life, say in any of our appliances which use mechanical forces when they run. And in most of those materials, the when conventional modeling approaches are used, they are assumed to be continuum. What do I mean by continuum? By continuum, I'm showing a simple LM sheet. If you have a sheet in your hand, which is of a very large size, which usually is in many of industrial applications, say. But if you look at the microscopic details, it is, I mean, at the crystal level, it is nothing but composed of some atoms which are arranged in a particular order. But if you look at the two lengths, so one length is the distance between, let's say, two neighboring atoms. That is, let's say, L microscopic length, which is designated as L micro. And other length scale is the experimental length scale. That is roughly the length scale at which the experiment or the particular material is used. And as you can see, that the two length scales are very, very different. The experimental length scale is too large as compared to a microscopic or the atomic length scale. So because this disparate nature of the two length scale, one can actually safely assume that that this particular sheet of metal is not really, it is formed by the atoms, but we can assume that the atoms are too close to each other, and we can assume that it's a one thing. There is no gap in the sheet as such from a modeling perspective. And for such systems, actually, this approach works very, very well. And you can easily see, I mean, a lot of the mechanical appliances actually use such this approach to model, and they work very well. And I mean, they are extremely successful. However, if we try to use the same approach for bioengineering applications, actually, then we face a challenge. And that is, here the two length scales are not very different. So here again, if we consider say a fibrous scaffold, then the microscopic length scale is when there are a couple of length scale which are of microscopic nature. So one microscopic length scale can be the diameter of the fiber, or other can be not not the diameter of the fiber, but the roughly the length of individual fiber which are there in the scaffold. And then the other length scale, that is experimental length scale, is roughly the length of. So as you can imagine that these two length scale in all of the tissue engineering applications are not very different. You may have some experimental scenario where, let's say, the diameter of, let's say, of nanometer size, and cells are tens of microns. In that case, the length scale is too different, but not always. And similarly, you can also have the other extreme where the fiber can be of, let's say, 100 of micron thickness, or even millimeter, a fiber of a diameter of 1 millimeter, and cell is just a couple of microns. In that sense, that is the other extreme. But that extreme is all. But these two extremes are also not as different as we have in case of a let's say a metallic sheet versus the atomic separation. So here, in case of tissue engineering applications, these length scales are not very different. They are somewhat close to each other. That means we cannot assume the fibrous scaffold as a continuum when we try to model its behavior. In addition to that, we also have another challenge, that is the fibrous, but these materials, especially the fibrous materials, due to the techniques they are fabricated, say electrospinning. Then even though we can have rough control over the structure of the over the arrangement of the fibers, but we cannot have a very precise control over it. So one can generate scaffold with random or a random or aligned fiber arrangement, but you cannot have an perfectly aligned fiber system, or you cannot have a fiber arrangement with a given geometry of the fibers. So these are the two biggest challenges actually which prevent us from using the continuum approach to model such systems. So this is again just to reiterate the thing that because the microscopic length scale is comparable to cell size, so in case of fibrous materials, we cannot use the continuum assumption, and similarly the structure also needs to be taken into account. So in order to handle these two challenges, we actually use two approaches. One is a peridynamics approach, which is a very not very old, which is a very recently developed method to study the brittle or the fracture mechanics of different materials. And second is the discrete fiber modeling, which is also known as Mikado modeling. So I will just give a brief description of how these two methods work and how they are different. Okay, so first, in case of first, I will describe how does peridynamics model work. What is the basic idea of it? So consider this is a simple. This is some scaffold or some body where some forces are acting on it from externally applied forces, or there are some cells on it where cells are applying the forces, and this leads to the deformation of this particular system. And the point which is marked as R with the red dot, it moves to some other location which is given by this particular function. Then, so if I go back to the conventional continuum approach, then when one tries to understand the mechanical behavior of such material using continuum modeling, they only take into account the local interaction of these points. So if you focus on the red, the red point, then in continuum modeling, we will only worry about how much is the displacement of its very neighboring point on the material, uh, only, which is confined to local interactions. But in case of peridynamics, we do not limit ourselves to the local interaction, but we can also take into account the non-local interactions. So as you can imagine, in case of fibrous material, you can have a fiber which goes from one point to other point, which can be which can be at a very far distance. So in order to take into account the presence of such long fibers, we have to take into account this non-local interactions. So that, and in addition to that, since I already mentioned that the structure of the material actually may affect, not may, but it definitely affects the mechanical behavior of 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 these systems. That means you also have to incorporate the structure of the fiber arrangement in the model somehow. So the way we try to do it, we do not include in this peridynamics approach, we do not include the exact details of each and every fiber in the system, each and every fiber of the geometry. We do not do that. Instead, what we do is we consider a statistical description of the fiber arrangement, and we take that statistical description, we plug this statistical description in the model. So how does it? So if you look at the plot, the curves which are shown at the left hand side, so that actually shows the probability density of fiber as a function of the orientation of the fiber. So theta is the orientation angle. So as you can see that in case of an aligned fiber, the most of the fibers will be aligned roughly at the same angle. So you can see that is shown by the red curve, where the peak can be seen at say pi over 2. However, in case of a random fiber arrangement, there is no preferred direction. So the probability density associated with each and every direction is basically same. That's why you get the flat blue curve. So we actually plug in these curves or these probability density functions into the model. So where do these, so how does these functions or these probability density functions fit in the model? So this is just to, you should not, so this is just to give you an idea how does peridynamics model work. So in case of a quasi-static loading, that is, if we are not worried about deformations which happen at a very fast rate, then we can actually obtain the response of the matrix just by minimizing this energy functional. So this energy functional has actually three contributions. So these three contributions come from, so first one, which is shown in red, it comes from the elongation of the fiber. So elongation of the fiber can happen only for a straight fiber. So if there is a fiber which is straight and you if you try to stretch it further, it is going to elongate. However, if a fiber is not straight and then you try to elongate it, to you stretch its two ends, then it just changes its shape. The length of this fiber is not going to change. So that contribution come in the form of the fiber bending, which is shown in green. And the third contribution, which is shown in blue, that is due to the fusion between any two fibers. So if you can see, I'm trying to show you here. So let's say these two are the fibers and they are joined at this particular location. And if the material, when this particular scaffold deforms, this angle between the two fibers may change. So if the angle changes, then there is some energy associated with the change in the angle, and that is taken into account by this fiber fusion energy. So actually, another thing what I'm trying to show here is this particular function p theta, which you can see. So this particular function p theta actually takes into account the arrangement of the fibers, whether they are arranged randomly or they are arranged in a particular order. So that is taken into account by this particular function p theta. And as you can see the second expression, which is ue plus ub. So that is nothing but integral all of the fiber area. So the way it is written is this particular expression captures the total energy of the fibrous matrix, which is then minimized. So in that sense, what we get is at the end, when we minimize and get what the deformation or the response of the matrix is, then this response actually gives us the average response. This gives us the average response of a fibrous matrix, which has this statistical properties. So in that sense, this peridynamics approach gives us the average behavior of a fibrous matrix with a given statistics. Okay, so this is the first method. Now, second method is the discrete fiber model. So this is a very straightforward and a sort of a brute force model. So in this, what we do is we deposit the fibers and in a particular domain. So here, so this is a rectangular space, and we can actually put fibers they can be straight. So here, for simplicity, I'm showing only the straight fibers, but they can also be one can also take into account curved fibers if one is interested. And we calculate where the fibers are intersecting, and by this deposition of many fibers, we can actually generate a geometry of such line segments which are connected at these red joints. Again, by following the same approach, that is that is that is that is we calculate the response of the whole matrix as the collective response of all the fibers. So the only difference between this particular approach, which is discrete fiber model, and the previous one, which is the peridynamics approach. So here, the response which we get, that depends on on the particular geometry of the fiber, as you can see. So if we, let's say, this shows only the one particular arrangement of the fibers. So one can have a different fiber sample, different sample which may have a different arrangement of the fiber. So for those two matrices, the response may be a little different. So in that sense, discrete fiber model actually gives us structure specific response, and peridynamics gives us an average response. So this is just a brief idea about the methods which are used. So now I will show you some of the results which are so from now on, the results which I'm showing. So almost all of the results are obtained from both of the methods to see if they are obtained from both of these methods. So I will not specify which method is used for which particular result. So this is just to see whether the models are working or they agree with the experiment. So we calculate the response of the fibrous matrix against a uniaxial elongation with two different degrees of fiber fusion, and we compared that with the experimental measurement of the matrix response, and we find that there is qualitative agreement with the between model and experiment. So as you can see, that the agreement is only qualitative, but not exactly quantitative, because for these particular plots we have not tried to fit the data to obtain any particular parameter, but we went with a pre-specified probability density functions, and just to see whether there is a qualitative agreement or not. And we also calculated the Young's modulus and the shear modulus of such a system. So the top panel actually shows the dependence of Young's modulus on fiber arrangement and fiber fusion, and the bottom colored plot shows the shear modulus as a function of those two parameters. So y-axis shows the degree of fiber alignment. So if you remain here, low value of sigma theta means that the fibers are aligned, and high value of sigma theta means fiber are randomly arranged. So as you can see that in case of aligned fiber, the response or the Young's modulus is pretty high, and similarly, the higher value of higher degree of fiber fusion also makes the matrix stiffer. However, when we calculated the shear modulus for the same system, we found there is an opposite response. That is the fiber with a random arrangement of the matrix with the random arrangement of the fiber shows a stiffer response. And reason for that is that in case of perfectly aligned fibers, when the shear strain is applied, then for certain arrangement or certain preferred directions, the matrix does not resist at all. So when you average over different configurations, you get a very weak response or very soft response. Yes. Again, we try to work out the effect of this non-local interactions, which I mentioned earlier. What is the effect of the non-local interactions on the mechanics of such systems? So in this particular plot, actually, there are two information which I would like you to focus on, and one is the x-axis, that is the sample aspect ratio, that is the width of the sample divided by its length. And second information is the color. So if you follow any one of the curves, say red curve, then you can see that as the sample aspect ratio is increased, the Young's modulus of the system actually increases. So that means the Young's modulus is not constant, but it depends on the size of the sample or the width of the sample, which is not there at all in case of the materials which are modeled as continuum. So for a continuum material, the Young's modulus is a fixed quantity. It does not depend on the size of the sample at all. And similarly, you can also see that with increasing degree of fiber fusion, the matrix becomes stiffer. So a closer look actually showed us that this particular observation is due to the fact that when the sample is not too wide, that is the small values of lambda. In that case, the load bearing fibers are not that many, which is shown by a schematic at the right hand side in the bottom panel. So there are so when the fiber sample is of width 2W, then there are some fibers which are from one end to the other end. But when the same sample is divided into two, then those fibers actually do not span the total length of the sample. That means they cannot actually sustain any load, and that's why you get a you get a softer response. Now, in addition to this macroscopic response, which we can measure in a mechanical testing machine, you can also have to look at what is the distribution of the fibers which are actually load bearing, and that actually also shows a sample size dependence in it. Additionally, we also have an observation that even though the if we have two fiber samples with two different arrangements, one is the random fiber arrangement, other is the aligned fiber arrangement, then it is possible to obtain a macroscopic response, that is the one we get when we try to measure it using mechanical testing machine. So we can have two different fiber samples which will show same macroscopic response, that is shown by the two red curves here, but their microscopic behavior is completely different, as you can see from here. So the density of the load-bearing fibers or the tension in the fiber is the distribution of the fiber tension is completely different in these two systems. That means the sample with same macroscopic response can have very different microscopic behavior. So how does all of this translates into the interaction of such fibrous materials to with the cells? So if you look at the interaction of any biological cells with scaffolds, then in many of the cells try to form, depending on the chemical nature of the fiber material, the cells try to form some ligand receptor bonds, and which eventually leads to focal adhesion and the formation of stress fibers. And through stress fibers, cells actually apply forces on the substrate, and through the application of such forces, cells sense the mechanics of the material. So in order to understand what is the local microscopic properties of such fibrous material and its dependence on the structure of its material, What we try to look at is the response of a square sample of a fibrous matrix against a point load which is applied at the center. So here you this is the condition. So in the first sample, the top one, all the four boundaries are fixed, and here only two boundaries are fixed. And then the plot which I will show now, they will actually show this particular sort of a spider plot where the red line, each red line actually shows the displacement which is applied in this particular direction, and the corresponding blue line segment shows the force or the resistance force which is generated by the matrix. So you can see that the response of the fibrous matrix depends on two factors. One is the location of the forces, where location on the matrix where the force is applied. So you can see that at the very center, the response of the matrix is very symmetric. So it is a very. However, if you come to a point which is close to one of the edges, then the response of the matrix is not symmetric at all. And similarly, there is also dependence on the fiber arrangement, which you can differentiate if you compare the plot of random fibers and aligned fibers. And this actually is also experimentally seen that in case in this particular fact that the matrix properties actually depend on the boundary conditions which are applied on the sample. So this has also been seen experimentally that near a free edge, the response of the matrix is very soft. So that means the cells do not experience too stiff a matrix, and that's how they do not spread too much. However, when a particular edge is fixed and a cell is located near the fixed edge, then cell experience a higher elasticity and then try to spread along those directions. So this shows that the elasticity which is experienced by the cell depends on cell location, the direction of the applied force, as well as on the boundary condition. So this just shows the microelasticity or the microscopic elasticity of the scaffold. Now, how does this translate when we try to see the response of the matrix when a cell comes in contact with it? So here's a very simplistic representation of a cell, where cell is represented by two opposing point forces, also known as force dipoles. So when we try to put this particular cell at the center of a matrix where the two edges are fixed at this particular orientation, which makes this, and we calculated what is the displacement field and the degree of fiber alignment, we found that the fibrous matrix gets displaced by a large amount at the two extremities of the cell. And this actually also matches with the experimental measurements on a reported experimental measurement. In addition, we also find that in case of a random fiber arrangement, when the cell comes in contact with the fiber arrangement, when the cell comes in contact with this particular scaffold, due to the forces which are applied by the cells, the geometry of the scaffold also changes. So that means the cellular forces also lead to the remodeling of the fibers. So here in this particular plot, the red region shows that the fibers are more aligned in this region and this region as compared to this blue region. And finally, when we try to look at the effect of the alignment of the fiber or the fiber structure on the response of the cell, what we found is that when cell is placed at different angles, so here alpha is the angle at which the cell is placed, and we try to simulate these models by varying this angle alpha, that is the cell orientation, relative to fiber orientation. So here the direction of the aligned. So this is an aligned matrix where the fibers are aligned diagonally in this direction, and we calculated the energy of the whole system in the presence of the cell, and we found that there is a local we found that there is a local minima as well as a maxima. And what happens is that cells try to minimize the energy, and that's why they prefer to align in the direction of the fibers. And this is also been seen experimentally by many groups, where the response of the cell is seen in the form of an aligned cell, where the alignment of the cell remains parallel with the alignment of the fibers. So this is so okay. So that's all I wanted to show. So this is just a summary that what I have tried to show you, or hopefully I have tried to convince you, is that the continuum modeling, the traditional continuum modeling, is not really, it's not always appropriate to understand the mechanics of fibrous biomaterials. And that means that means when one is trying to understand the mechanics of such system, non-local interactions also have to be taken into account. And due to these non-local interactions, we have seen that these fibrous scaffolds demonstrate some sample size effects, which are not seen in, let's say, metals. And the effect of these factor comes also in the picture when a cell comes in contact with such scaffolds in the form of the dependence of mechanics on cell location, direction of the cell force, and applied boundary conditions, and many other parameters which I have not shown today. So that's all. And before I end, I would like to acknowledge some of the people who have been part of this particular work. So I'm pretty sure many of you are know very well Prasoon and Professor Katti, who, I mean, both of them were integral towards the experimental part of this particular work, and Lake Dr. Anupampal and Sovan Laldas, who were also part of this work at the theoretical and modeling end. And that's all, and thank you for your time. That's it.
Any questions from the audience?
Hello.
Yes, sir.
Yeah, Suhail, I just wanted to understand in one of the slides at microelasticity, you talked about that the cells is, in this slide, you talked about that the cells is going to act on the, suppose I'm just asking a condition, if there is a freestanding membrane, freestanding nanofibrous structure, and one is the nanofibrous deposited on the hard substrate. If the cells are going to land upon those two different locations, is the microelasticity would still play a role?
Okay, so I will repeat the question and tell me if I understood correctly. So you are saying there are two systems. In first, the fiber are deposited, let's say, are suspended somehow, and in other system, the fibers are deposited on a rigid substrate, right?
Yes, true.
Okay, yes. So actually, there have been some work in this direction, and not on the fibrous scaffolds, but in case of say some polymeric gels. So it turns out that the cells can actually sense the presence of the stiff substrate up to a distance. So it will depend on the thickness of the fibrous mat you have. So if the thickness of the fibrous mat is too much, then cell will basically cannot sense that there is anything beneath it.
Okay.
Yeah. So there have been some experimental as well as modeling works on this. Yeah. If you
Okay, thank you, sir.
So there is a question for you in the chat box. I'll read it out for you. And the question is, one cell type can have different orientation in different tissues. How can orientation be optimized in engineered constructs?
Okay. So if I understand correctly, so this is the same cell which can have different orientation in different tissues. So actually orientation can mean different things. So I do not know which orientation you're talking about. So one can be just a physical orientation, that is the cell is not really cell is asymmetric in shape, and that asymmetry is in a particular orientation. So the input which I can give, which will be purely from the mechanics point of view. And from mechanics point of view, it seems that that if you want to have cells in a particular orientation, then one has to modulate the microscopic elasticity, which is shown at the current slide, in the tissue engineering constructs. So if you want to have a single cell which is oriented in different direction depending on the location of the tissue, then you have to arrange the fibers in a manner such that the microscopic elasticity follows that particular pattern. So that is the input which is from the mechanics point of view. But there may also be some ways to, there may be some other biochemical ways to do it, which I'm not really expert of, so I will not comment on that. I hope this answers the question.
Yeah, hopefully. Any further questions?
Hello, sir. So the fiber model
All
which
right,
you
then.
consider.
Thank you for sharing your knowledge with us here today. We'll move on to the next speaker. We have now our last speaker of the day.
Thank you, Sohail Rajvi. Thank you for accepting the invitation as well as enriching our participants with your knowledge. Thank you so much.
Thank you.
In a
Thank
short
you for
span of
inviting
time,
me.
you have accepted our request and you have given a wonderful talk. Thank you so much.
Oh, thank you very much.
All right. So we have now our last speaker of the day, Dr. Mohit Kumar Jolly, Assistant Professor, Biosystem Science and Engineering Department, Indian Institute of Science, Bangalore, Karnataka, who would be discussing on computational systems biology of cancer. How can mathematical models help us understand cancer better? Dr. Mohit Kumar Jolly leads the Cancer Systems Biology Group at the Center for Biosystems Science and Engineering, Indian Institute of Science. He has made seminal contributions to decoding the emergent dynamics of epithelial mesenchymal plasticity in cancer metastasis through mathematical modeling of regulatory networks implicated in EMP. His work has featured on the cover of Journal of Clinical Medicine, Cancer Research, and Molecular and Cellular Biology, and he won the 2016 iBiology Young Scientist Seminar Series, a coveted award for communicating one's research to a diverse audience. He is an elected fellow of the Indian National Young Academy of Sciences and serves as secretary of the Epithelial Mesenchymal Transition International Association, and is also co-chair of Mathematical Oncology subgroup at Society for Mathematical Biology. I now request sir to please begin with the presentation. Over to you, sir.
Is my screen visible?
Yes, sir. It's visible.
Is my screen visible?
Yes, sir.
Yes, sir, it's visible.
It's visible.
Okay, great. Let's put this in presentation mode. Thank you very much for the kind introduction and the invitation to present some of our work at this bioengineering conference. I think this is a very important opportunity to talk about different engineering disciplines coming together to solve biological questions. And today what I'll be talking about is one of the central tenets in any engineering discipline, that is developing mathematical models or replica of the system that we are trying to design to achieve a certain objective. However, here we are designing mathematical models to first understand the progression of cancer better, and with the hope that these models can give a better handle at designing the therapies that are being used in the clinic. So I'd like to thank the organizers for putting together this excellent meeting and this opportunity. Now, cancer, as many of you may be already aware of, is basically a disease that is referred to as emperor of all maladies. It is the uncontrolled growth of these abnormal cells in the body. Every cell in the body has a mandate to grow only a few number of cell divisions and then it dies, but somehow due to various reasons, when some cells are able to continue to proliferate in an uncontrolled manner, which is what leads to cancer and disruption of the function of different organs of the body. Cancer, once it initiates in a group of cells in a given organ, it typically, when we are talking about solid tumors, it no longer remains restricted to the initial organ. but also spreads to other organs, and this process is known as metastasis. The time scale that you see here can be different for different cancers, but what I'm trying to emphasize is the acceleration in the process that happens once cancer begins to
The
spread
time scale that
from
you
a
see
primary
here
tumor
can be
to
different for
secondary tumors in different organs. Over the past couple of decades, we have made some fantastic progress in diagnosing cancer early. So now there are tests for both men and women, for instance, for prostate cancer and breast cancer, respectively, early screening for them, in identifying the genes that are involved in this process, and also in identifying different risk factors such as smoking causes lung cancer. But as you would see, all this progress restricts itself to the initial stages of cancer progression, or to some extent even prevention of cancer. We have not really made any major breakthroughs when it comes to metastasis, which still remains the cause of 90% of all cancer-related deaths. And how does cancer spread from one organ to another is largely through this fantastic set of freeways that we have in our body called the blood vessels. So imagine a tumor in a given organ. It gets onto the blood vessels around it and then travels cancers, but what I'm trying to organs of the body and continues to form. We have not really made any major. Now, you would think of metastasis as a highly efficient process, but what literature reports is that it's actually a highly inefficient process with extremely high rates of attrition in the entire process. So what we try to understand is that what are the properties of that small percentage of cells that are able to form a metastasis eventually that leads to 90% of deaths of cancer patients. So I'm going to try to present metastasis as a dynamical process where one can define the different axes as different cellular properties and try to decode the spatiotemporal dynamics of that property depending on the position of the cell and the properties that it has along all these different axes that are listed here. And then can we try to understand how exactly are cancer cells managing to evade the different attacks which are being made by the immune system and the drugs? How are they able to dynamically change their ability to migrate and invade? Because once they're in a primary tumor, they are not moving. They're actually stuck in a specific 3D geometry very tightly to their neighbors. But once they start moving, then of course they have to loosen some of their bonds and gain the ability to migrate. And once they reach a distant organ, they again have to undergo the exact opposite transition. So how are they switching between these different properties in a very coordinated manner in space and time and across these different axes is the major problem that we are trying to address. Now, when we talk of cancer, clearly the idea of mutations and mutational signature comes in very dominantly. But so far, there is no unique mutational signature that has been identified for metastasis. There are mutational signatures for primary tumor growth, but in metastasis, there is none of them, despite the huge amount of money and effort that are being spent. And that to me makes a lot of sense, because metastasis, the way we think about it, is a highly dynamic process where cells have to continue to adapt. And mutations are typically hardwired, irreversible solutions that once has occurred will be propagated from generations to generations. So it locks the cells in a specific state and therefore potentially is not necessarily beneficial for the process of metastasis. So what I'm going to talk about today is a systems approach. Many of you may already be aware of it. The idea being that if you look at some engineered systems, these are systems that we have designed, and there are various different feedback loops, computers. We already know the design manual. We know how these components are connected because, as I said, this is the bottom-up approach. We design the system to achieve a specific objective. However, if you look at even the simplest biological systems, they tend to be much more complicated as compared to the most complex engineering systems that we are aware of. And unfortunately, there is no design manual available. We don't know why molecule A interacts with molecule B instead of interacting with molecule C. Sure, it does some function, but why exactly things are connected the way they are is not really written anywhere. So we try to decode that, and eventually, with the hope that we can understand to try to fix these systems. Now, if you look at most cancer biology literature, and here is an example from one very highly cited paper in the field of cancer biology, we typically see these kinds of networks, these schematic, cartoonish representation of things. To some people, this might be sufficient to say that we understand what exactly is going on. But if a question is asked, well, which node will you perturb, which edge will you perturb if you want to reduce metastasis, then we really have no clue as to what exactly to do. Because this cartoonish representation, this schematic, has no information whatsoever on the time scale, on the length scale, on strength of regulation, on combinatorial effects. So let's say if there are two nodes, A and B and C, all of them affecting this node, then is this an AND gate? Is there a sum of them? A product of them, etc. All that information is just completely missing. So we are shooting in the dark for all practical purposes. And these assumptions that are often hidden in this black box kind of approach without having any of these quantitative parameters can have unpleasant surprises in the clinic. So for instance, in the early 2000s, when the anti-angiogenesis therapy was being tried out, which means that if you can block the blood vessel growth of cancer, that is sufficient to reduce cancer growth. What was seen was the patients who received this therapy actually had worse outcomes than patients who did not receive this therapy. Only now we understand that the reason that was happening was because the cells to whom we are blocking the blood vessel growth actually begin to metastasize faster. So clearly cancer is a dynamic system. It's evolving in response to different stresses that we are putting on it, and therefore we need to understand the dynamics of it and not just static snapshots per se. This is the last sentence of the most cited review in the field of cancer biology called Hallmarks of Cancer, where the authors are emphasizing that cancer biology is far away from the stature that is there in other fields such as chemistry or physics, where one develops mathematical models, makes predictions, and then there is this iterative cycle that continues. And 10 years later, when they wrote Hallmarks of Cancer, the next generation, this is the last sentence from that review, and clearly you see that there is the underlying organizing principles are still far from being understood. So that's the focus of our lab. We develop mathematical models working closely with experimental cancer biology groups and also clinicians with the goal that can we help explain the existing experimental data and then, of course, make new predictions that can be tested in the lab. So we go back and forth. This is a bidirectional communication and iteration that continues to happen. And clearly this cannot happen from expertise coming from only one discipline. So we tend to collaborate with people coming from various different disciplines, and that interdisciplinary attitude is, background is also seen in our own group. We have students from physics, from mathematics, engineering, bioinformatics, and molecular and cellular biology backgrounds who sort of work together to try to address some of these aspects. So I'd like to acknowledge all my fantastic set of collaborators right away before I delve into the details. So the goal of our lab, as I said, is to develop such predictive mechanism-based mathematical models that we can identify what is the fitness signature of these cells which undergo metastasis, what is the signature of cells that drive this therapy resistance. So largely we focus on three aspects currently. One of them is that if you look at the molecular networks that are involved, how do those networks enable this idea of phenotypic plasticity, which basically means that cells can continue to switch back and forth between multiple phenotypes and continue to adapt. We also look at sort of in a more theoretical aspect as to try to understand the design principles of such networks, which basically means that why are networks designed the way they are. So here we are looking at specific molecules and what those molecules may be doing to an existing network, and then going back to our experimental colleagues to test the prediction. And this is sort of relatively more abstract, where we ask these questions, why this network structure? Why not 1,000 others that are possible using the same nodes, using the same edges? And then eventually, of course, we want to drive the wheel to have clinical applications, both in terms of identifying biomarkers and also having new therapy ideas eventually. So these are the set of students who have been working on some of these, and we have been looking at some of these aspects that I'll talk about today. And there's some other new students who still need to find their way into this maze as to which group they would want to belong to. So in the context of metastasis, the dogma in the field had been that there are these epithelial cells in the body, which is the most common cancers. If you think about, say, lung cancer, prostate cancer, liver cancer, stomach cancer, breast cancer, all of them are epithelial organs, which means cells do not have the property to start moving or invading by their own. They actually are settled and tightly forming a bond with their neighbors. But somehow they are able to undergo this transition to a more mesenchymal phenotype, which have the exact opposite properties, that they can move and they can invade, but they do not typically adhere to their neighbors. So the idea had been that there is this transition that cells undergo from E to M called EMT, which typically forms the first step of metastasis. And once they reach the other organ, they undergo the exact opposite transition called MET, because now they no longer need to migrate or invade, rather they actually need to settle down and form tumors. So this is a very binary paradigm. Either cells don't move at all or they move as single cells. And this is what had been there in the literature before we started looking into it. It's a very binary kind of picture. These are snapshots taken from various different influential reviews that have been written over a decade. And clearly you see that even if people talked about this third state, which is somewhere in between, it was referred to as metastable, which basically means that cells cannot stay there for a long period of time. So we started with a very simple question, that is EMT and MET, is this a binary process, or can you have a state in between? And if yes, then what is the biological meaning and biological implication of that state? So what we did here was, again, just putting together the different parts of our aeroplane together. For instance, we sort of went through the literature, tried to identify what molecules are known to drive EMT in multiple different cancers, what molecules are known to inhibit EMT or drive MET in multiple different cancers. Do we know how they connect to each other based on what is reported in the literature? And that is this small network that we started with. These are the more mesenchymal ones, these are the more epithelial ones. So we then developed a mathematical model. We converted this schematic into a set of coupled ordinary differential equations that represent the interactions that you see here. So each variable here is a species here, and each of them has this production rate, each of them has this degradation rate, and then they have these terms which correspond to microRNA regulation, because some interactions are happening at a post-transcriptional level and some which are happening at a transcriptional level. Long story short, the predictions of our models were the following. So here the x-axis is some EMT inducing signal, the y-axis is some measure of EMT-ness. The solid lines are stable states which will convert to biological phenotypes, and the dotted lines are unstable states. So what we said was that, yes, of course, there are these two epithelial and mesenchymal phenotypes that we know in the literature, but also there is a third state which is possible, which may have the property to integrate adhesion and migration, and therefore show traits such as collective cell migration. So it can be a stable state, it can be a stable phenotype, it need not be a metastable or intermediate that cells show only transiently. The other prediction was that now, of course, you have cells which are completely epithelial, or cell lines, cell populations which are completely mesenchymal, but it would not be surprising if you were to find a cell population that has phenotypes from all different kinds of cells. So again, having the same genetic background, but still you have this non-genetic layer of heterogeneity or phenotypic layer of heterogeneity that is built in. And the third prediction was that cells can actually switch back and forth, even without necessarily having an external induction here. So we collaborated with a couple of groups, and others also have experimentally provided independently validation of all these three different predictions over the past couple of years. So here, for instance, these are lung cancer cells which are stained for E-cadherin, which is an epithelial marker, and vimentin, which is a mesenchymal marker, in green and red respectively. And you can see that many cells actually seem to have both red and green, suggesting that it's a hybrid phenotype at a single cell level, and that phenotype is maintained over 2 months. So it's not just a static snapshot, but this is something which can be maintained in culture as well for further analysis. We did flow cytometry-based experiments where we tried to identify this heterogeneity. We measured the same two molecules that I just talked to you about in breast cancer, in prostate cancer, in lung cancer, and in colorectal cancer cell lines. And again, you clearly see that there is this heterogeneity that exists. These are experiments from yet another different setup where they're again using vimentin and EpCAM, and you see this heterogeneity, and when you sort them, these cells, and grow them independently, you see that over a period of 2 weeks, there is some switching that is observed. Please bear in mind, there is no EMT induction signal that is given. It's just that there are multiple states and they can go back and forth. So over the past years, the EMT field has now begun to realize more and more, with more and extensive data coming in vitro, in vivo, and also in the clinic, that EMT is clearly not a binary process. There are one or more states in between. And interestingly, the cells which are most metastatic ones are not the ones which are completely epithelial, not the ones which are completely mesenchymal, but the ones which are somewhere in between. So again, metastasis as an output of EMT as an input is a non-monotonic response. It maximizes somewhere in between and then it decreases again. There has been a burst of mathematical models that have come up in the past couple of years, each using a different network, each using a different modeling strategy, some doing similar to what I mentioned to you in terms of ordinary differential equations, other using sort of Boolean modeling similar to logical rules in computer science, where if A is inhibiting B, so sort of B is equal to naught of A. If B is on, then A is off. So it's a very discrete kind of setup. So we wanted to see that if you look at all these different networks, is there something specific about the topology itself that allows for one or more of these hybrid states? And this work was led by my PhD student Kishore, together with two summer interns we had from Burhan from IIT Madras and Vishnu from IISER Trivandrum. So we looked at these different networks that you see here and many others and simulated them in two different manners. One is, as I mentioned, the Boolean approach, where we are using logic gates, and others in which you're writing down differential equations and randomly sampling parameters. And for every parameter set, you're randomly sampling initial conditions as well. So this is a parameter agnostic approach, and this is a parameter independent approach because there are no parameters to play around with here. And the idea was that if we get similar results using each of these different approaches across these different networks, what that suggests is that there is something very fundamental to the way they connect, that the degree to which they connect might not necessarily be the most essential thing to worry about. But if you just look at how they connect, and if you're able to perturb those connections, then that might be sufficient to change the ability to metastasize. So these are the two different formalisms that I already talked to you about. And then we simulated these different networks using both of these strategies, and saw that this is the frequency distribution of the different steady states or the phenotypes that we saw. You clearly see, irrespective of the method used, the two most dominant states are the same. We further quantified this using this metric called JSD, which is Jensen-Shannon divergence. What this metric does is that if there are two distributions that completely overlap, this value is 0, and if they don't overlap at all, this value is 1. Clearly, you can see that for this network and for other networks, this value is closer to 0 than to 1, suggesting that, again, there is information present in network topology itself. Now, since this is all simulations, you can do a lot of experiments in silico. The type of experiments we did here was that we took our network and then either deleted an edge or added a hypothetical edge where one did not exist, or changed the sign of an edge, which means that ZEB, which was inhibiting GRHL2, now we said, let's see what happens in the hypothetical case when instead of inhibition, there is an activation that is going on. Again, irrespective of the approaches that you use, you are able to find the perturbations that are making the maximum difference in terms of steady-state distributions, and that also ends up to be the same, irrespective of the method used. Again, further suggesting that topology itself has a lot of information that is potentially largely independent of parameters. And this trend of correlation of these values in Boolean approach and receipt approach was seen to be positively correlated across different networks. Now, our major interest here was that what exactly allows cells to switch back and forth. So what we noticed in the perturbations which were actually taking the distribution furthest away was that there were some feedback loops which were broken, and a very specific type of feedback loops. So for instance, if you look at this network here, ZEB inhibits MIR200 and MIR200 inhibits ZEB back again. So if you look at this path, this is a net positive feedback loop because negative multiplied by negative is positive. So ZEB can bring down MIR200, and when there will be no MIR200 to bring ZEB down, ZEB will continue to stay on. So similarly, we counted how many net positive feedback loops are there of varying lengths and how many net negative feedback loops are there of varying lengths, and see if that correlates with the ability of a network to give rise to multiple steady states. What we observed was a very clear trend that the higher the number of positive feedback loops in any of the network, the higher was the tendency to show multiple steady states for the same parameter set, suggesting that if you want to break the ability of a cell to switch to yet another state, then you need to break a feedback loop, and a very specific type of feedback loop per se. That was our prediction, and there was actually a beautiful experimental validation of this exact prediction that we had made using the sophisticated technology that has come up now of CRISPR-Cas9. So the same feedback loop that I just introduced you to, and we had modeled earlier, they were able to break this feedback loop by deleting the binding site of ZEB in the promoter region of microRNA 200. So now this feedback loop is broken. What happens as a result of this? This is the wild type cells with this particular circuit, which is wild type. These are the cells with this particular circuit, which is mutant. X-axis, and this is an in vivo experiment. The x-axis is days after these cells were injected in mice, and y-axis is the number of metastasis that was seen. So what you, and please bear in mind that the y-axis is on a log scale. So what we saw was, or what the authors saw was that when you break this feedback loop, their ability to increase metastasis in response to the signal which is abundant in the tumor goes down significantly. Now, unfortunately, this paper does not go into too much details of a mechanistic reason for this particular observation, but this very well fits with what we have been talking about, because the possible reasons here is that if you break a feedback loop, we are actually gotten rid of a set of states. So therefore, the cells have lost their ability to adapt to a varying degree. Another potential reason is that if you have cells doing different things in a population, they may be cooperating with one another, and there are examples of this seen in cancer metabolism, for instance. So if you get rid of one state completely by breaking this feedback loop, again, you have reduced the chances of cell-cell cooperation and therefore the fitness of the population overall. So just summarizing this part, as I said, the ideas earlier, EMT was thought of as a very binary process, and what we proposed is that there are one or more states in between, and not only those states exist, but they are actually the most fit, the most plastic, and the most metastatic, therefore. And one way to get rid of them is by breaking these feedback loops. Because currently what is going on in the clinic, people are trying to inhibit EMT, but depending on the efficacy of this inhibitor, there may be an enrichment of cells in hybrid. If it's not completely blocked, if it's only partially blocked, then you might see more cells in hybrid, which is actually counterintuitive and counterproductive in this case. So therefore, one strategy can be to make sure that cells stay where they are, they lose their ability to go left, go right on the EMT axis, and that is what we are proposing, which was highlighted in a recent review that this can be actually a very novel idea for the clinic. Switching gears, I'll quickly tell you about one other story, which focuses on small cell lung cancer, which is an exceptionally aggressive disease with 5-year survival rate of less than 7%. Just to give you a perspective, 5-year survival rate of breast cancer is more than 95%. So you can clearly see the discrepancy that exists in this case. There's no new treatment strategy in past 5 decades. There's no targeted therapy that exists for this cancer, and it metastasizes very early. Possibly that is a major reason why the survival rate is so low. What is known about this cancer? We know of its existence for almost 100 years now. We know where it originates from. We know what mutations are seen in patients of this particular cancer, small cell lung cancer, or SCLC in short. We have cell lines, we have xenografts, we have genetically engineered mouse models, and we have high dimensional data being collected continuously on all of these. Again, this is a case where most, if not all, patients have the similar mutational profile. So again, mutations are not really explaining why you see a heterogeneity or different states present in SCLC, because clearly there have been multiple phenotypes that have been experimentally reported, and mutations are just not sufficient to explain that. Here is an image from a study a couple of years ago, where we know that there are, broadly speaking, at least two different ways that these cells can grow. So there are different classes of SCLC cell lines, one that grow in this particular morphology and the other which grow in this yet another morphology. What we know from recent in vivo studies is that if you inject only one of them in mice, then metastasis is not as efficient. But if you put both of them together, then you see a burst of metastasis. Again, suggesting there are potentially some ideas of cooperation that is going on between these different cell states. What we now know, just like EMT, is that earlier there was this classification of what was called neuroendocrine versus non-neuroendocrine, or any or non-any in SCLC, but we know that there are also hybrid states which are seen in this particular case, and this binary picture is no longer sufficient. So the work I will present to you is led by two undergraduate students, one majoring in biology, the other majoring in physics, Laksha and Uday, together with my PhD student Kishore. So the question we asked here was, again, does the idea of multi-stability, having multiple states, which I talked to you about in the context of EMT, is that also applicable here? Can we look at network that is known for SCLC? Can we simulate that network? Can we see multiple states? And again, can we say something about the network topology itself, which enables this particular behavior? So this was the only network that we could find in the literature that is available for SCLC. The red lines show inhibition, the green arrows show activation, and each of them is a transcription factor or a master regulator of one of the other. Now clearly you can see this network is much larger as compared to the EMT networks that you saw, which were only 5 to 10 nodes. This network is 33 nodes and 350 plus edges. So in the small networks of EMT itself, we were seeing 4, 6, 8, 10 states. So we expected that in this network, we will probably see thousands, if not millions of states. But we saw only 4 states. And that was very surprising to us. We did multiple simulations, started with different number of initial conditions to make sure whatever we are seeing is not an artifact. We did Boolean simulations, and we also did this continuous simulations. And again, these were among the top dominant states that were seen in continuous simulations, suggesting that this particular network gives rise to 4 states. Now, we wanted to see if these 4 states is specific to this topology, or is this something which sort of just exists randomly? So what we did was we looked at this network and we shuffled different edges, an example of which, a simple example of which is shown here. So let's say if A activates B and C inhibits D, so this is your wild type network. Now in a shuffled network, or in a random network, A is activating D and C is inhibiting D. So you have basically flipped the output nodes. The total number of nodes are the same, the total number of edges are the same, the total number of green edges are the same, the total number of red edges are the same. The out degree of a node is the same, the in degree of all the nodes is the same. But what is different is that in degree of in or out degree of red, or those aspects. So those can be different, but we did as the best as we could to conserve different control for different features. We did 1,000 such shuffled networks of that wild type network I showed you a couple of slides ago, and simulated, and then saw that each of those 1,000 networks were giving rise to a much larger number of states. The x-axis, this is a histogram, the x-axis is the logarithm on the base 10 of the number of states, and the y-axis is the frequency. And this dotted red line is the wild type case, saying that for the wild type, you had 4 states, which is what I just talked about. But for all the other random networks, you had many, many more states. Interestingly, none of these 4 states was seen in any of these other random networks, suggesting that there's a complete disjoint set of solutions that we saw. So next we wanted to ask that now if you take this network and make single edge perturbations, you either delete an edge which would be similar to a CRISPR-Cas9 experiment, or you change the sign of H. You make a negative to a positive, so instead of A inhibiting B, now it's activating B, or vice versa, and see what happens to the frequency of the solutions. Now, in 345 cases out of 357, if you delete that edge or you change the sign of that edge, there is no difference whatsoever, suggesting that this network is highly, highly robust. So what exactly is so special about this network topology? So then we looked at all these network solutions obtained from Boolean and received, and what we observed was that if you do pairwise correlation of every different variable with everyone else and plot them in this diagonal matrix, it looks like there are these two sets of genes which are very well positively correlated with one another, within a group, and they are negatively correlated across different groups. We again wanted to check if this is something specific to the network topology, or is it also seen in a random network. So what we did was, again, we summed up the values in these two triangles and we subtracted the value in the rectangle because these values are negative. This is the wild type case, these are the random networks case. You clearly see the random networks just do not have this feature at all. This trend was also seen in experimental data, where you again see these two teams of players that are potentially inhibiting each other. That's why you see the strong negative correlation, but activating one another. That's why you see such a strong tinge of red, which is seen here. But please, again, this is all correlation. This is nothing to do with causation. So if X and Y are negatively correlated, that does not mean that X inhibits Y necessarily, or Y inhibits X. None of them, it's possible that none of them is true. So next, what we did was that this is the same matrix that I showed you here. This received one. It has just been reflected about the diagonal. So now you have a square instead of a triangular matrix. And then we went to the network topology itself and defined what we call influence matrix. So you basically go from every node to every other node, and see how many paths exist, and then sort of quantify the net effect of node A on node B. So when we do that, we see that this gives very similar results as compared to the correlation matrix. Now, getting this metric, we did not do any simulation. We just looked at the connections in the file itself, suggesting that yes, it is these connections which underlie that actually give rise to these results. So saying that it looks like there are two teams of players. This team of players is activating one another. This team of players is also activating one another, and then they are playing this mutual inhibition. And this A inhibits B, B inhibits A. This is a very common topology that is seen in different developmental cases when a cell has to decide from a bipotent progenitor to become cell type A or cell type B. And again, if you remember the EMT circuit, microRNA 200 and ZEB also inhibit each other. So hidden in this complex network is a very simple principle that there are, instead of just having one A and one B, there are teams of A and teams of B which are inhibiting each other. And we showed using further quantification that if you again look at random networks, this property is just completely lost. So this is something specific to that network topology. We were able to reduce, based on these trends that we observed, we were able to reduce that highly complex network into just a small network. And this small network gives the same 4 states that we have been talking about. Now, let's look at the experimental data. So these are 2 molecules which have been known in the SCLC literature for quite some time in their ability to explain the data. ASCL1 and NEUROD1 explain the heterogeneity in the data. So you clearly see, based on simulation data, they are negatively correlated with one another. Then we looked at some 50 plus cell lines in SCLC and did hierarchical clustering based on just these 2 genes, and saw very clear 4 clusters. And those 4 clusters are actually lying in 4 different quadrants of this coordinate axis, saying that yes, there are cells which express both of them. There are cells which express neither of them, and then there are cells which express NEUROD1 and low in ASCL1, or the cells that express ASCL1 and are low in NEUROD1. So again, these 2 belong to the 2 teams that we were talking about. We used yet another clustering method and yet again found that 4 was the optimal number of clusters, and those 4 clusters were actually following the same pattern. So it sort of um, does not depend on the clustering method that is used. And if you go back to all the solutions that I showed to you earlier, these are indeed the 4 solutions: AS double positive, double negative, A positive, N negative, and A negative, N positive. Just summarizing this part, we said the idea being that the phenotypic heterogeneity in SCLC, which has been seen and shown to play an important role in metastasis, can emerge because the network itself allows for multiple states, and that network has a very simple hidden topology. That there are 2 teams of players, and again, you need not look at a very large number of genes. You can look at a small set of genes which can explain these behaviors. I would just end with this thought that let's say if you have 3 different boxes, and one box which has 6 white balls, get as 3 red balls, and then you have a box with 3 blue balls. In how many ways can you pick up 1 white, 1 red, and 1 blue ball? So clearly there are 6 ways to pick up a white ball, 3 ways to pick up a red ball, and 3 ways to pick up a blue ball. And since these experiments are independent, the number of ways basically continue to be multiplied. What has this to do with metastasis? So if there are 6 or more EMT states that people now talk about, if there are 3 or more stemness states, if there are 3 or more metabolic states, and you can continue to see this property of multi-stability across different axes. So cells are actually playing a very important game here, because if you are defining fitness of metastasis at a single cell level, then they need to coordinate all these different properties together. So out of 6 cross 3 cross 3 cross whatever number of cases that we are talking about, they can only select a few states. So how are they choosing, or is this underlying message that the cells which are able to metastasize are the ones which are able to achieve fitness on each of these different axes independently, and also coordinate those things in a very rigorous manner with themselves. With that, I would like to thank the members of my lab, and I'll be more than happy to take questions. And if you have any more questions about the group, I'll be more than happy to be contacted through email or via Twitter. And as I said, we do encourage and invite people coming from different backgrounds, because each of them has a different perspective to contribute to this complex problem that still remains to be solved in the clinic. Thank you so much.
We'll move on to the question and answer session. I request attendees to please put forward the questions.
Thank you, Mohit, for such a wonderful talk. I just wanted a very naive question. The question is that, is the cell metastasized as a single cell or a group of cells?
Thanks, Prasanathan. That's an important question. Both have been seen. What has been noticed is that when cells move as a cluster, they form many more metastases. A disproportionately high number of metastases. So clusters are typically 5 to 10 cells large, but they form 50 times more metastases as compared to single cells. But whether these clusters are formed before they leave the tumor or in the bloodstream, both evidence have been presented as well.
Okay, and following question is that if they are moving as a cluster, so if they are in the form of a cluster, there may be some ECM around them, I suppose. So if it is true, is the ECM is playing any role in promoting their metastatic ability?
So what has been reported is that matrix stiffness can promote EMT. This has been seen in vitro, and also, I think, if I remember correctly, in at least some organoid models, if not in vivo as well, that the ones which are more aggressive tend to have a higher stiffness.
Okay, okay. Thank you, Mohit. Thanks a lot.
Thank you, Prasanna.
So there is a question for you in the chat box. I'll read it out for you. Why do we see selective secondary tumor chosen by a primary tumor? Example, GBM chooses lungs for secondary tumor site and breast cancer chooses bone.
Okay, so the question is that why is there a preferential metastasis to certain organs depending on the primary tumor where the cancer originated? So the most widely accepted current thought
Wants
process in the
research to a
field is
diverse
this overall
audience.
idea of origin and soil theory, which was proposed in
And shown to claim
1889
important
by
role.
each of those thousand networks were giving rise to, saying that just as seed
Encourage
needs
can
a
pick up one white, one
compatible
red,
soil
and
to
two
grow.
blue balls.
Similarly,
There are 6 ways to pick up.
cancer cells coming from one organ might need very different properties as compared to those coming from a different organ to grow. So the idea is that possibly cancer cells go to all different organs which are in their route, but they settle down, they are able to settle down in only a few of them, and that largely depends on the compatibility of the secondary site with the properties of the primary tumor cells.
Hope it answers the question. Any further question?
I have a couple.
All right.
Mohit, can you hear me?
Yes, sir. Please go ahead. Yes.
Actually, I think first question I've already asked you a long time back that the ODE equation you write for the EMT state.
Mm-hmm.
So, is there any progress in knowing what causes the the mixed phenotype? I mean, how does the mechanics play the? How does mechanics is connected to the ODE's equation which you write? Is there any progress or not yet?
There is some internal progress on that. So the more mesenchymal cells are capable of secreting matrix stiffness enzymes that can play a role in collagen cross-linking and therefore matrix stiffness. We are in the process of and as a result, we will see soon that matrix stiffening cell can get triggered to EMT. So we are trying to establish this biochemical biomechanical feedback loop currently autonomous manner and then see what is it properties as compared to the ones where there is only biochemical signaling, just as we have done so far.
Okay, thanks. Another question about the last part. Actually, I was thinking about the coarse graining, the whole large network which you already did.
Right.
Is it possible to do this coarse screening based on only topology, or do you have to do the simulation, the whole simulation, and then only you can derive what will be the appropriate coarse grain system?
So here we first had to do the simulations to identify the groups that need to be coarse grained. But I don't think it is essential to do simulation. Still working on what exactly is the minimum amount of input we need to get.
So it is not. You don't think it will be possible through only the topology?
It may be.
It may. Okay. 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 That's all. Thanks.
Thank you.
Any further questions? All right, sir. Thank you so much for serving us as one of the speakers today.
Thank you so much.
Thank you, sir. I would also like to thank Professor Nivedita Patra, the chairperson for this session, for sharing her valuable time with us here today. With this, we wind up this session and we'll be having a oral session. But before that, we'll be taking a short break. I request all the attendees to please stay connected until we are back. Thank you.